Long before humans existed, dinosaurs were the dominant animals on Earth. They first appeared approximately 230 million years ago during the Triassic period and continued to thrive through the Jurassic and Cretaceous periods. For more than 160 million years, they occupied nearly every type of environment, including dense forests, vast plains, deserts, river valleys, and coastal regions. This means that dinosaurs lived on Earth for a period far longer than humans have existed. During their reign, dinosaurs evolved into an incredible variety of species. Some were small enough to fit in a person's arms, while others grew to lengths greater than a school bus and weighed many tons. Plant-eating dinosaurs such as sauropods used their long necks to reach vegetation high above the ground, while predators like tyrannosaurs developed powerful jaws and sharp teeth for hunting. Their diversity allowed them to adapt successfully to different climates and habitats across the globe. Dinosaurs were not just one type of animal, but a vast group with unique characteristics and lifestyles. Some traveled in herds for protection, others hunted alone, and many developed specialized features such as horns, armor plates, crests, and feathers. Fossil discoveries show that dinosaurs lived on every continent, including Antarctica, which at the time had a much warmer climate than it does today. Throughout their long history, dinosaurs survived numerous environmental changes, including shifts in climate, changing sea levels, and geological events. Their ability to adapt and evolve enabled them to remain the most successful large land animals on Earth for millions of generations. By the late Cretaceous period, dinosaurs had become highly diverse and widespread, filling ecological roles that ranged from top predators to giant herbivores and fast-moving omnivores. The dominance of dinosaurs over such an immense span of time demonstrates their remarkable success as a group of animals. Their long-range shaped ecosystems around the world and influenced the evolution of countless other species that lived alongside them. Fossils, footprints, nests, and eggs discovered by scientists continue to provide valuable insights into how these extraordinary creatures lived, grew, interacted, and flourished during their time as Earth's ruling animals. The asteroid that struck Earth 66 million years ago was enormous, with scientists estimating its diameter to be between 10 and 15 kilometers. To understand the scale of this object, imagine a mountain-sized body traveling through space at incredible speed. An asteroid of this size would have stretched across a large metropolitan area and would have been visible from a great distance if observed from Earth before impact. Although many asteroids orbit the Sun, only a small number are large enough to cause global environmental consequences, making this particular asteroid one of the most significant objects in Earth's history. Size alone does not fully explain the asteroid's destructive power. What made it especially dangerous was the combination of its massive size and extraordinary velocity. Scientists estimate that the asteroid was traveling at roughly 20 kilometers per second, or about 72,000 kilometers per hour, when it struck Earth. At such speeds, even a relatively small object can release tremendous energy, but an asteroid measuring 10 to 15 kilometers across carried an amount of energy that is almost beyond comprehension. The asteroid was likely composed of rock and metal, similar to many objects found in the asteroid belt between Mars and Jupiter. As it traveled through space, it remained largely unchanged for millions or even billions of years. Eventually, gravitational interactions altered its orbit and placed it on a collision course with Earth. Unlike smaller meteoroids that burn up in the atmosphere, an object of this size would have passed through the atmosphere with little loss of mass before reaching the surface. The energy released upon impact has been estimated to be equivalent to billions of atomic bombs exploding simultaneously. The collision generated temperatures so extreme that rocks melted and vaporized instantly. Huge amounts of material were blasted into the atmosphere, and a massive crater formed within minutes. The impact transformed the surrounding environment almost instantly, creating conditions that would affect the entire planet. Scientists study the size of the asteroid by examining the dimensions of the Chicxulub crater and using computer simulations to model the impact. By comparing crater size, rock deformation, and the distribution of debris around the world, researchers can estimate the asteroid's original diameter and velocity. These studies consistently suggest an object within the 10 to 15 kilometer range, making it one of the largest impactors known to have struck Earth in the last several hundred million years. An asteroid of this magnitude had enough mass to influence global systems rather than merely causing local destruction. The effects extended far beyond the immediate impact area. Dust, ash, and vaporized rock were spread around the world, affecting atmospheric conditions on a planetary scale. The amount of material ejected into the atmosphere was directly related to the asteroid's immense size and the tremendous force of the collision. The dimensions of the asteroid also helped scientists understand why the extinction event was so severe. Smaller impacts have occurred throughout Earth's history and often caused regional damage, but they did not trigger worldwide ecological collapse. The asteroid that struck 66 million years ago was large enough to disrupt climate patterns, alter ecosystems, and affect life in both terrestrial and marine environments. Its size placed it within a category of impact events capable of reshaping the course of biological evolution. Research into this asteroid continues to provide valuable insights into planetary defense and the risks posed by near-Earth objects. By studying its size, composition, and impact effects, scientists gain a better understanding of how similar objects behave and what consequences might result if a large asteroid were to threaten Earth in the future. The estimated diameter of 10 to 15 kilometers remains one of the key factors that explains the extraordinary power and global influence of the impact event that ended the age of the dinosaurs. When the asteroid struck Earth 66 million years ago, the effects were not limited to the impact site alone. The collision triggered a chain of catastrophic events that spread across the planet, causing widespread destruction on a scale never witnessed in human history. Among the most devastating consequences were enormous earthquakes, giant tsunamis, and widespread wildfires. These disasters occurred almost immediately after the impact and contributed significantly to the environmental crisis that followed. The moment the asteroid collided with Earth's surface, it released an immense amount of energy into the surrounding rocks. This energy generated powerful seismic waves that traveled through the planet's crust. Scientists estimate that the resulting earthquakes were far stronger than any earthquake recorded in modern times. Some researchers suggest that the impact may have produced seismic activity equivalent to a magnitude 10 or even greater. These earthquakes would have shaken vast regions of the Earth, causing landslides, ground fractures, and the collapse of natural landscapes far from the impact site. As the seismic waves spread outward, they disturbed both land and ocean environments. Coastal regions experienced intense shaking, while underwater geological structures were destabilized. The force of these earthquakes may have triggered additional geological events, including submarine landslides and changes in volcanic activity. Evidence preserved in ancient rock formations indicates that the Earth's crust experienced enormous stress as a result of the impact. At the same time, the asteroid struck a region that was partially covered by shallow seas. The collision displaced massive volumes of seawater almost instantly, creating gigantic tsunamis. These waves were unlike anything seen in modern history. Near the impact site, some tsunami waves may have reached heights of several hundred meters. The waves traveled across entire ocean basins, carrying tremendous energy as they moved outward in all directions. Sunlight is essential for life on Earth because it provides the energy needed for photosynthesis. Plants, algae, and many microscopic organisms rely on sunlight to produce food and oxygen. However, the dense cloud of dust and debris blocked a significant portion of the sun's rays from reaching the Earth's surface. Scientists believe that this reduction in sunlight may have lasted for months, years, or even longer in some areas, depending on atmospheric conditions and the concentration of particles. As sunlight decreased, temperatures around the world began to fall. This period of cooling is often referred to as an impact winter. Similar to how volcanic eruptions can temporarily cool the climate by releasing ash into the atmosphere, the asteroid impact produced an even more dramatic effect. The thick atmospheric veil reflected and absorbed sunlight, preventing solar energy from warming the Earth's surface. As a result, many regions experienced colder and darker conditions than they had before the impact. The reduction in sunlight had immediate consequences for plant life. Photosynthesis slowed dramatically or stopped altogether in many ecosystems. Plants that depended on regular sunlight struggled to survive, and large numbers began to die. Forests, grasslands, and other plant communities were severely affected. Since plants form the foundation of most food chains, their decline created a ripple effect throughout ecosystems. Marine environments also suffered from the lack of sunlight. Tiny organisms called phytoplankton, which live near the ocean surface and rely on photosynthesis, experienced massive population declines. These microscopic organisms are a critical food source for many marine animals. As phytoplankton populations decreased, the effects spread through the marine food web, impacting fish, marine reptiles, and other ocean-dwelling species. The dust-filled atmosphere also affected weather patterns and precipitation. Scientists believe that the altered climate may have caused unusual rainfall patterns, changes in seasonal cycles, and disruptions to ecosystems that had evolved under relatively stable environmental conditions. Many species were unable to adapt quickly enough to these sudden changes, increasing the severity of the extinction event. Evidence for this period of darkness and atmospheric disruption comes from geological records found around the world. Scientists have studied layers of sediment, chemical deposits, and fossil evidence that indicate a dramatic environmental shift following the impact. Computer simulations and climate models further support the idea that sunlight was greatly reduced for an extended period, creating conditions that were hostile to many forms of life. The prolonged blockage of sunlight was one of the most important factors in the global ecological crisis that followed the asteroid impact. By disrupting photosynthesis, cooling the climate, and weakening food webs on land and in the oceans, the atmospheric dust and debris helped transform a single impact event into a worldwide environmental catastrophe that affected nearly every ecosystem on Earth. The survival of nearly all life on Earth depends directly or indirectly on plants. Plants are known as primary producers because they create their own food through the process of photosynthesis, using sunlight, water, and carbon dioxide to produce energy-rich sugars. This process forms the foundation of most ecosystems and food chains. When the asteroid impact 66 million years ago filled the atmosphere with dust, ash, and debris, sunlight reaching Earth's surface was greatly reduced. As a result, photosynthesis was severely disrupted, causing widespread damage to plant life around the world. In normal conditions, plants absorb sunlight every day to generate the energy they need to grow, reproduce, and survive. Forests, grasslands, wetlands, and other ecosystems depend on a steady supply of sunlight to maintain healthy plant communities. After the impact, however, the thick cloud of airborne particles blocked much of the sunlight that plants relied upon. Many species were suddenly unable to produce enough food to sustain themselves. As weeks and months passed, large numbers of plants began to weaken and die. The effects were felt across many different environments. On land, trees, shrubs, ferns, and flowering plants experienced major declines. Entire forests may have suffered extensive damage as reduced sunlight limited growth and prevented the production of new leaves and seeds. Plants that had evolved under stable environmental conditions were not prepared for a prolonged period of darkness and cooling. Many ecosystems that had flourished for millions of years faced rapid collapse. Aquatic environments were also heavily affected. Lakes, rivers, and oceans contain countless microscopic photosynthetic organisms, including algae and phytoplankton. These organisms are just as dependent on sunlight as terrestrial plants. When sunlight levels dropped, their populations declined dramatically. Because phytoplankton form the base of many marine food webs, their disappearance created serious consequences throughout ocean ecosystems. The decline of plant life had a direct impact on herbivores, the animals that feed on vegetation. Large plant-eating dinosaurs, such as hadrosaurs, ceratopsians, and sauropods, required enormous amounts of food every day to survive. As vegetation became scarce, these animals faced increasing difficulty finding enough nourishment. Starvation became a growing threat, particularly for large species with high energy demands. As herbivore populations declined, carnivores were also affected. Predatory dinosaurs depended on herbivores as their primary food source. When plant-eating animals became less numerous, predators faced food shortages as well. This created a cascading effect throughout ecosystems, where the decline of one group led to the decline of another. Food chains that had supported diverse communities of organisms for millions of years began to break down. The disruption extended beyond dinosaurs. Many insects relied on specific plants for food and reproduction. Small mammals, reptiles, birds, and amphibians also depended on plant-based ecosystems either directly or indirectly. As plant populations shrank, countless species lost their habitats, food sources, and ecological relationships. The interconnected nature of ecosystems meant that damage to primary producers quickly spread throughout entire biological communities. Scientists refer to this process as a food chain collapse, where the loss of organisms at the base of the food web affects every level above them. Fossil evidence and ecological models suggest that this collapse played a major role in the mass extinction event. Species that could not find alternative food sources or adapt to rapidly changing conditions faced a high risk of extinction. The loss of sunlight did not simply reduce plant growth for a short period. It fundamentally altered the flow of energy through ecosystems. Since plants are responsible for capturing solar energy and making it available to other organisms, their decline meant that less energy was entering food webs worldwide. This reduction in available energy weakened ecosystems on a global scale, affecting terrestrial and marine environments alike. The widespread death of plants and the resulting disruption of food chains transformed Earth's ecosystems in profound ways. Communities that had existed for millions of years were destabilized, and many species were unable to survive the resulting shortages of food and habitat. The collapse of plant populations became one of the key mechanisms through which the asteroid impact triggered a global extinction crisis, affecting organisms at every level of the ecological pyramid. The mass extinction event that occurred 66 million years ago was one of the most severe biological crises in the history of life on Earth. Scientists estimate that approximately 75% of all species disappeared during this period. This means that nearly 3 out of every 4 species living on the planet became extinct. The event was so widespread and destructive that it affected life in the oceans, on land, and even among microscopic organisms. It marked the end of countless evolutionary lineages that had existed for millions of years. Extinction is a natural part of Earth's history, and species have always appeared and disappeared over time. However, most extinctions occur gradually and affect only a small number of organisms. The event at the end of the Cretaceous period was different because it happened on a global scale and within a relatively short geological period. Entire ecosystems were disrupted, causing species from many different groups to vanish almost simultaneously. The extinction affected organisms of all sizes. Large animals such as dinosaurs were among the most visible victims, but they were far from the only ones. Many marine reptiles, including mosasaurs and plesiosaurs, disappeared from the oceans. Numerous species of fish, mollusks, plankton, and other marine organisms also became extinct. On land, a variety of plants, insects, and smaller animals experienced significant population declines or vanished completely. One of the most heavily affected groups in the oceans was the ammonites. These shell-bearing marine animals had thrived for hundreds of millions of years and were highly successful throughout much of Earth's history. Despite their long evolutionary success, they did not survive the environmental upheaval caused by the extinction event. Their disappearance is one of the most well-known examples of the widespread losses that occurred during this period. Marine ecosystems suffered especially severe damage because many food webs depended on photosynthetic organisms such as phytoplankton. When sunlight was blocked by dust and debris in the atmosphere, phytoplankton populations declined dramatically. Since these microscopic organisms formed the foundation of many ocean food chains, their loss affected countless species higher up the food web. The resulting ecological collapse contributed to the extinction of many marine animals. Terrestrial ecosystems experienced similar challenges. The decline of plants reduced food availability for herbivores, which in turn affected predators. As habitats changed and resources became scarce, many species were unable to adapt quickly enough. Large animals were particularly vulnerable because they often required greater amounts of food and larger territories to survive. Species that depended on stable environmental conditions found it difficult to cope with the sudden changes occurring around them. Despite the enormous losses, not all life disappeared. Approximately 25% of species survived the extinction event. These survivors included certain birds, small mammals, crocodilians, turtles, amphibians, insects, and various plant species. In many cases, survival was linked to characteristics such as small body size, flexible diets, the ability to shelter underground, or the capacity to live in aquatic environments. These traits helped some organisms endure the harsh conditions that followed the impact. The extinction of such a large percentage of Earth's species dramatically altered the course of evolution. Ecological niches left vacant by extinct organisms became available for surviving species to occupy. Over millions of years, new groups evolved and diversified, creating ecosystems very different from those that had existed before the extinction. The disappearance of so many species opened opportunities for mammals and birds to expand into roles previously dominated by other animals. Scientists continue to study fossils, geological evidence, and ecological patterns to understand why some species survived while others did not. By examining extinction and survival patterns, researchers gain valuable insights into how ecosystems respond to environmental crises. The fact that around 75% of Earth's species became extinct demonstrates the extraordinary scale of the event and highlights how vulnerable even successful organisms can be when faced with rapid and dramatic changes in their environment. One of the most significant consequences of the mass extinction event 66 million years ago was the disappearance of all non-avian dinosaurs. For more than 160 million years, dinosaurs had been the dominant land animals on Earth. They occupied a wide range of habitats and evolved into thousands of species with different sizes, shapes, and lifestyles. From enormous long-necked herbivores to powerful predators, dinosaurs were among the most successful groups of animals in Earth's history. However, the environmental catastrophe triggered by the asteroid impact brought their long reign to an abrupt end. The term non-avian dinosaurs refers to all dinosaurs except birds. Modern scientific research has shown that birds evolved from a group of small feathered dinosaurs and are therefore considered living dinosaurs. When scientists say that the dinosaurs became extinct, they are specifically referring to the non-avian species that disappeared at the end of the Cretaceous period. This includes famous dinosaurs such as Tyrannosaurus rex, Triceratops, Ankylosaurus, and Edmontosaurus. Before the extinction event, dinosaurs were thriving across much of the world. Fossil evidence shows that many species were diverse and successful right up until the end of the Cretaceous period. They inhabited forests, river valleys, floodplains, coastal regions, and other environments on multiple continents. There is little evidence that dinosaurs as a group were already dying out before the asteroid impact. Instead, many paleontologists believe they were still flourishing when the catastrophe occurred. The environmental changes that followed the impact created conditions that were extremely difficult for large dinosaurs to survive. As sunlight was blocked by dust and debris, plant growth declined dramatically. Herbivorous dinosaurs, which depended on vegetation for food, faced increasing shortages. Because many of these animals required enormous amounts of food each day, even a temporary reduction in plant availability could have serious consequences. As herbivore populations decreased, carnivorous dinosaurs lost their primary prey and also began to suffer from food shortages. Large body size may have made many dinosaurs particularly vulnerable to the changing conditions. Bigger animals generally require more food and often reproduce more slowly than smaller animals. During a period of environmental instability, these factors can reduce a species' ability to recover from population declines. As ecosystems collapsed and resources became scarce, many dinosaur populations likely experienced rapid declines that they could not reverse. The extinction of non-avian dinosaurs was not necessarily instantaneous. Although the asteroid impact occurred on a single day, the environmental effects continued for months, years, and possibly decades. During this period, dinosaurs faced a combination of challenges, including habitat destruction, climate change, reduced food availability, and ecosystem collapse. These pressures gradually eliminated populations across different regions of the world. Fossil records provide clear evidence of the disappearance of non-avian dinosaurs at the boundary between the Cretaceous and Paleogene periods. Dinosaur fossils are abundant in rocks dating before the extinction event, but they are absent in younger rock layers. This sudden disappearance is one of the strongest pieces of evidence for the scale and severity of the extinction. Similar patterns can be observed in many other groups of organisms that did not survive the environmental crisis. While the extinction marked the end of the non-avian dinosaurs, it did not erase all traces of their evolutionary legacy. Birds, which evolved from small feathered theropod dinosaurs, survived the catastrophe and continued to evolve. Today, there are more than 10,000 species of birds living around the world, making them one of the most diverse groups of vertebrates. Their survival provides a direct link to the dinosaur era and demonstrates that part of the dinosaur lineage endured even as their larger relatives vanished. The disappearance of all non-avian dinosaurs fundamentally transformed Earth's ecosystems. For millions of years, these animals had occupied key ecological roles as herbivores, predators, scavengers, and ecosystem engineers. Their extinction left numerous ecological niches vacant, creating opportunities for surviving groups of animals to expand and diversify. The loss of the non-avian dinosaurs therefore represented not only the end of a dominant group of organisms, but also a major turning point in the history of life on Earth. The extinction of the non-avian dinosaurs 66 million years ago was one of the most important turning points in the history of life on Earth. While the event caused the disappearance of countless species, it also created new opportunities for the organisms that survived. Among the most significant beneficiaries were the mammals. Although mammals had existed alongside dinosaurs for millions of years, they had generally remained small and occupied limited ecological roles. After the extinction, the disappearance of dominant dinosaur groups left many habitats and food sources available, allowing mammals to expand and diversify in ways that had never been possible before. Before the extinction event, most mammals were relatively small creatures, often no larger than modern mice, rats, or small cats. They lived in a world dominated by dinosaurs and were often restricted to specialized ecological niches. Many were nocturnal, meaning they were active at night, which may have helped them avoid predators and competition from larger animals. While mammals were diverse, they did not dominate terrestrial ecosystems in the way dinosaurs did. When the mass extinction removed many of the largest animals from Earth's ecosystems, enormous ecological opportunities became available. Habitats that had once been occupied by giant herbivorous and carnivorous dinosaurs were suddenly vacant. Food sources that had been heavily utilized by dinosaurs could now be exploited by surviving animals. Mammals were among the groups best positioned to take advantage of these changes because they possessed a variety of characteristics that helped them adapt to changing environments. Over the millions of years that followed, mammals underwent a remarkable process of evolutionary diversification. Different groups evolved to occupy a wide range of ecological roles. Some became large herbivores that fed on plants, while others evolved into predators, omnivores, insect eaters, swimmers, gliders, and climbers. Mammals gradually spread into habitats across continents, filling niches that had previously been unavailable. The early Paleogene period, which followed the extinction event, witnessed an explosion of mammalian diversity. Fossil evidence shows that mammals increased in both size and variety during this time. Species evolved specialized teeth, limbs, and body structures suited to different lifestyles. Some developed long legs for running, while others adapted for digging, climbing trees, or living in aquatic environments. This adaptive radiation allowed mammals to become one of the most successful groups of animals on the planet. Among the many branches of mammalian evolution were the ancestors of modern primates. Early primates evolved traits such as grasping hands, forward-facing eyes, and enhanced depth perception, which were useful for life in trees. Over time, these primates diversified into numerous species and spread into different environments. Their evolutionary history would eventually lead to monkeys, apes, and eventually humans. The development of larger brains played an important role in the evolutionary success of many mammal groups. Increased intelligence allowed mammals to develop more complex behaviors, improve problem-solving abilities, and adapt to changing environments. In the lineage that eventually produced humans, brain size and cognitive abilities expanded significantly over millions of years, enabling advanced social behavior, communication, and tool use. The rise of mammals was not immediate but occurred gradually over tens of millions of years. Evolution is a slow process driven by natural selection, environmental change, and genetic variation. The extinction of the dinosaurs did not directly create humans. Rather, it removed ecological barriers and created opportunities that allowed mammalian evolution to proceed in new directions. Without these opportunities, the evolutionary pathways that eventually produced humans might have been very different. Fossil discoveries from around the world reveal how mammalian life changed after the extinction event. Scientists have uncovered evidence of early mammals evolving into a wide range of forms, including ancestors of modern elephants, whales, horses, bats, rodents, carnivores, and primates. These fossils help researchers trace the complex evolutionary journey that followed the disappearance of the dinosaurs. The transformation of Earth's ecosystems after the extinction event reshaped the future of life on the planet. As mammals expanded into newly available ecological niches, they became increasingly important components of terrestrial and aquatic environments. Their diversification led to the development of many of the animal groups that exist today and ultimately set the stage for the emergence of human beings millions of years later. The extinction event therefore represents not only the end of the age of dinosaurs, but also the beginning of a new chapter in evolutionary history, one in which mammals became the dominant land animals and continued to evolve into an extraordinary variety of forms across the globe.